Chapter 2, Section 5, Digging Deeper, Forces in Earth's Crust, Types of Forces. In the Investigate, you observed models of folds and faults in rock layers using clay and styrene foam. You then compared these models to what you could see in geologic maps and cross-sections. This digging deeper will help you to understand how rock layers form and then can become folded or faulted. Earlier in this chapter, you learned that sedimentary rocks form from sediments that are originally laid down in almost flat horizontal layers. In many places on Earth, however, sedimentary and other kinds of rocks are not found in a horizontal position. Instead, they are tilted at some angle to the horizontal. Sometimes they are tilted so much that the layers are vertical. Let me scroll down a little bit. The tilting of the layers is a sign that they have been deformed by forces acting within Earth. The forces can cause the rocks to become folded. Folds are usually formed when rocks are squeezed together by compressive forces. The forces can cause the rocks to fracture and then to slip along the fracture surfaces. A fracture surface along which rocks slip is called a fault. Forces within Earth that cause folding and faulting are created by the movement of Earth's lithospheric plates. The plates move very slowly, 2 to 20 centimeters per year. However, over hundreds to thousands of years, great forces build up in Earth's crust. These forces are transmitted for long distances through the crust. As a result, folding and faulting can happen not only near the plate boundaries, but also in the interiors of the continents far from plate boundaries. 3 different kinds of forces can cause rocks to deform. They are tension forces, compression forces, and shear forces. As you saw in the Investigate, different types of forces have different effects on rock layers. Suppose you are holding a solid rectangular block between your hands. When you try to pull the block apart at its ends, you are exerting a tension force. When you push the ends of the block together, you are exerting a compression force. When you hold 2 opposite edges of the block and try to move them in opposite directions, you are exerting a shear force. In all 3 cases, if the force you exert is greater than the strength of the solid material, it deforms. It will deform either by fracturing or just changing its shape without actually breaking. The forces that are created in Earth's crust by the movement of lithospheric plates are often great enough to deform the rocks. In Figure 1, it shows the directions and effects of tension, compression, and shear forces. So here's your tension, compression, and shear. Forces, okay. Folding and faulting. What determines whether a rock is faulted or folded? It is partly a matter of temperature. In the previous chapter on plate tectonics, you learned that Earth's interior rises on average by 25 degrees centigrade per kilometer of depth. This rate is higher closer to plate boundaries. At lower temperatures, as in the upper parts of Earth's crust, rocks are brittle. They tend to deform by fracturing. In the lower parts of Earth's crust, the temperature of rocks is relatively high. When forces are exerted on rocks at high temperatures, the rocks tend to deform by changing their shape continuously rather than by faulting. Folding is an example of how rocks can change their shape continuously without breaking. This is shown in Figure 2. Whether a rock is folded or faulted is also a matter of time. If forces build up very fast, rocks are more likely to fracture. However, if forces build up very slowly, the rocks are more likely to change their shape without breaking. Figure 2 shows intense heat and pressure folded these previously horizontal sedimentary layers. So they were previously layered horizontally, and then the heat and pressure folded them. All right. Using models to investigate geologic structures. Geologic processes such as folding and faulting of rocks work over very long time spans. The folding of rocks cannot be observed in nature as it happens. The use of models helps scientists to understand the deformation of rocks. One such model used by geologists involves layers of colored wax and a special squeeze box to investigate the folding process. The box has a glass wall for viewing the wax from the side. One side of the box moves along threaded rods, creating a force on the wax as the walls close in on one another. Wax is poured into the box one layer at a time. A knob on one end of the box allows the wall of the box to be moved horizontally. This movement squeezes the wax from the ends. The model allows scientists to vary the rate at which the force is applied and the thickness of the various layers. The model helps them to create folds that can be seen in nature. From this, they are able to make interpretations about the forces that create folds. Faults. A fault can be formed by tension forces. These forces cause the rocks of the crust to be pulled apart. In that case, the body of a rock above the fault plane slides down relative to the body of a rock below the fault plane. So that's shown in figure 3. Wait, it says figure 3A. Hold on. Oh, figure 3A, right here. Okay. Faults of this kind are called normal faults. A fault can also be formed by compression forces. These forces cause the rocks of the crust to be pushed together. In that case, the body of rock above the fault plane slides upward relative to the body of the rock below the fault plane. Okay. Faults of this kind are called reverse faults. So far we have normal faults, reverse faults. When the fault plane is nearly horizontal, reverse faults are called thrust faults instead. When the fault plane is nearly horizontal, reverse faults are called thrust faults instead. When a fault is formed by the horizontal shear forces, the bodies of rock on either side of the fault plane slide past each other horizontally. Faults of this kind are called strike-slip faults. Movement on faults usually occurs suddenly after a long time without movement. The forces that cause the faulting build up very slowly. When they become greater than the strength of the rock, the fault moves. This relaxes the forces, which then slowly build up again. Major faults typically move only every few centuries. Most earthquakes are caused by sudden movement on faults. So figure 4, they're saying what kind of fault is shown in this photograph? Well, if we look up at the diagram, if we look up at figure 3, look at the fault. The fault is going up and to the right. So let's see if we can match that. It looks like look at where it was. It started here. You can see this band that started up here, but now this band is further down. So that'd be the normal. Okay, that's a normal. The left side moved down. Left side's further down. Okay, so that's a reverse. All right. Okay. Folds are especially common when the rock is layered. Like sedimentary rock and the layers, folds are especially common when the rock is layered. Like sedimentary rock, and the layers differ in their stiffness, which is the resistance to being bent. Here's a thought experiment. To show the effect of layering, make a square block of soft modeling clay and squeeze it together from opposite sides. It becomes compressed, but it does not form folds. Now make a block that consists of many thin layers of clay separated by index cards. Squeeze the block from opposite sides in a direction parallel to the index cards. The block then deforms by folding. Geoscientists who study folds label their various parts so they can communicate clearly about them with other scientists. The two sides of the fold that dip in opposite directions are called the fold limbs. Each limb dips towards where the fold has its maximum curvature, where the dip of the limbs changes the most. This line is called the hinge line. The axial plane is an imaginary surface that extends from the hinge to bisect the limbs of the fold. Scientists take measurements of the directions and dips of these and other parts of folds using a compass and a clinometer. Measurements are recorded on maps like those you examined in Part C of the Investigate. Let me scroll up a little bit so we can see this diagram as they're talking about it. Folds in Earth's crust are usually arranged horizontally. Folds whose limbs are concave downward are called synclines, which is shown in Figure 6A. So there's your syncline, which is called Seidling Hill in Maryland. See how it's concave? Okay, so the way that it's kind of like a U shape. So that is a syncline, and Seidling Hill in Maryland, in the state of Maryland, is an example of a syncline. All right, let's see what else it says here. 6A. So we just looked at 6A. Were we further up than that? Okay, synclines. Folds with limbs that are convex upward are called anticlines, which is shown in 6B. There's your anticline in Wyoming, in the state of Wyoming. All right. Single folds occur as do folds with a series of rock layers that have buckled in a complex way. Folds in rocks can be as small as centimeters or as large as many kilometers. Okay, so syncline, concave, anticline, convex. Plate tectonics and major regions of folding and faulting. The forces involved in lithospheric plate interactions produce features such as folds and faults. For example, when two plates carrying continental crust collide at a convergent plate boundary, a vast amount of stress is applied to the rocks. This stress causes rocks to deform. Figure 7 is a map showing the locations of Earth's major mountain belts. Okay, so you've got your North American Cordillera mountain belt, the Andes mountain belt, the different mountain belts, Caledonides, the Alps, the Atlas mountain belt, Ethiopian Highlands mountain belt, the Urals mountain belt, the Zagros mountain belt, Tian Shan mountain belt, Kolyma mountain belt, the Himalayan mountain belt, the Southern Alps mountain belt, and the Great Dividing Range mountain belt. And like they said, they're on some of the same mountain belt is on different continents and different islands. Okay. So some of the mountain belts are similar on different continents. Alrighty. Most of the world's, well, I'll scroll up because it's talking about that. I'll scroll up and show the figure. figure 7 because it does talk about figure 7. Most of the world's mountains occur in long belts that follow convergent plate boundaries. Mountains can be classified by the types of deformation that form them. For example, folded mountains often occur when rocks fold as two plates carrying continental crusts collide. Although faults also occur in these mountains, their folded rock layers are prominent features. The Appalachians, okay, hold on, let me show this while I'm talking about it. The Appalachians, the Alps, the Northern Rocky Mountains, the Urals, and the Himalayas are examples of folded mountains. Fault block mountains, on the other hand, form when large blocks of rock are uplifted between normal faults. In some parts of the western United States, the crust is slowly being uplifted. This is causing the crust to stretch and fracture, forming normal faults along the surface. So what did we say a normal fault was? Okay. Right here. All right. We go back down. Causing normal faults along the surface. Whole blocks of crust have been pushed up into fault block mountains. The Sierra Nevada of California, the Wasatch Range of Utah, and the Teton Range of Wyoming are all examples of fault block mountains. Okay, so that's within this range. Okay, let's see what they say. Volcanic arcs are often associated with plate collisions. Volcanoes are mountains that do not always contain folds and faults. Similarly, when gigantic batholiths are exposed at the surface, they may lack evidence of large-scale deformation.